Hey guys! In this video, I'm going to go over Euler's Runge-Kutta method. So first, I want to take a second and discuss what a Runge-Kutta method is. A Runge-Kutta method is used to solve ordinary differential equations. And basically what we're doing is we're using information from a known point to estimate the value at a new point or a future point that we want to calculate. And so all Runge-Kutta methods have the same base equation, which is given here. So we have yi plus 1, which is basically just notation for our new or our future point. We have yi, which is notation for our old or our previous point. We have h, which is the step size of this function. And this is pretty much always given to us. And then we have phi. And phi is the incremental function, or basically the slope. And phi is what changes for each type of Runge-Kutta method. So you'll need to memorize the equation to calculate phi for Hume's method, Euler's method, the midpoint method, whatever Runge-Kutta method you're using. So for Euler's method, phi equals the derivative dy dt evaluated at the previous point. And so that is how we get the base Euler's equation here. So as you can see, it's exactly the same as the base Runge-Kutta equation. It's just that I've replaced phi with dy dt. Okay, so now that you have a better understanding of what a Runge-Kutta method is, let's go ahead and solve an example problem. So I'm given the differential equation dy dt equals 2ye raised to the 0.5 t power with an initial value y of 0 equals 3 over the interval 0 to 2 and a step size h equals 1. And I need to solve using Euler's method. So the first thing I'm going to do is identify my givens. So I have my differential equation. I have my given initial value. I have my interval and my step size. So if we draw a line graph real quick, this is our lower bound, t equals 2. Or sorry, t equals 0. And then our upper bound is t equals 2. And then we have step size of 1. That means that we will have an intermediate step at t equals 1. And right now, we know the y value at t equals 0 is 3. And we don't know the y value at t equals 1 or t equals 2. So next I can go ahead and perform my first iteration. And this iteration is going to go from t equals 0 to t equals 1. So we're going from here to here. So if I look at my base Euler's equation real quick, I have yi plus 1 equals yi plus dy dt times h. And so h equals 1. yi is going to be the y value at 0. yi plus 1 is going to be the y value at 1. And that's what we're looking for. And then dy dt, we can solve at our previous point, which is 0, 3. And so that is actually going to be part A of our iteration, is to calculate dy dt. So dy dt equals 2 times the y value, which is 3, times e raised to 0.5 times 0 power. And that gives us a value of 6. So then we can take and substitute all of that information into Euler's equation. So yi plus 1 is going to be yi, which is 3, plus dy dt, which is 6, times 1, which gives us a value of 9. So the y value at t equals 1 is 9. Okay, we're not done yet because we haven't reached our inbound. So now we're going to perform a second iteration. And this time we're going to go from t equals 1 to t equals 2. So this time we're going from here to here. So if we look at our base Euler's equation, we have yi plus 1 equals yi plus dy dt h. So h is 1. yi this time is going to be the y value at 1, because now this is our new previous point. And then this time yi plus 1 is going to be the y value at 2, because now we're looking for the new point y of 2. And then dy dt is going to be evaluated at 1, 9. So let's go ahead and calculate that. Calculate dy dt. So dy dt equals 2 times 9 times e raised to the 0.5 times 1. And that gives me a value of 13.18977. So then I'm going to take that and substitute it back into Euler's equation. So yi plus 1 equals 9 plus 13.18977 times 1, which gives me a value of 22.18977. And this so happens to be our answer, because this is the y value at t equals 2. And that is our inbound. So that's it. I hope this video helped you guys better understand Euler's Runge-Kutta method.